Okay, so last thing I want to talk about today is what is Chapter 7 and why do we need partial derivatives? Because you should be okay with like basic, simple partial derivatives. Chapter 7 is called Nonlinear Systems. In the last two units that we've done, all of Chapter 5, we did things like, let's say, x prime equals 4, 3, -1, 5, x. You learned how to do eigenvalues, eigenvectors, phase plots, all kinds of stuff with that. We did it with inputs, monkeys, forces. Let me write what this really means. Remember, x is a stacked vector. In this case, it would be too tall. So we could write x1, x2, but instead I'm going to write x comma y is x. So what is this whole system? This would be xy prime equals 4, 3, -1, 5, x, which I could write as two equations. And I think this is how we did it when we were doing like what's it called, elimination, like ages and ages ago. But x prime equals 4. Oh wait, this should, let's see, this I should write that as xy. And remember when we multiply matrices, we go across and down. So this is representative of x prime equals 4 times this plus, because it's dot product-y thing, 3 times that. So I get 4x plus 3y. And y prime is -x plus 5y. So what I want you to see is that this is a linear system, right? It's a linear system of differential equations. There's no squareds, there's no sines, there's no cosines. X here is just all by itself. It's linear in x and y. I could add an f of t that is nonlinear, but that doesn't change the fact that this part of it is linear, and that's what we call a linear system, one in which the x's and y's, the variables over here whose derivatives are there, show up in a linear fashion here. So, what is a nonlinear system? Because that's what Chapter 7 is about. Well, let me write one. If I have, and remember, before I write it, this is the derivative, this is the derivative of x with respect to time. This is the derivative of y with respect to time. So, I could have something like dx dt is x squared minus 2x minus xy, and dy dt is equal to y squared minus 4y plus xy. And now these equations as a system, just like this was a system, are now representative of a nonlinear system. That should make sense to you. This part is linear. This part is linear. Here, x is being multiplied by y. It's not a linear piece. X is being multiplied. And here I got an x squared. So that's definitely not. You may be able to say, well, maybe that is linear. I'm not really sure. This is definitely not, right? So these guys are nonlinear systems. These are super practical, super applicable. This is actually like a competing species model from biology or ecology. And that's a lot of what we're going to focus on as we do all of these nonlinear systems. But they're super applicable and they show up all over the place. The rate of change of one species, it's the size of the population, is we use statistics and data and science to come up with this equation, and then we can do stuff with it. Same thing here. We figure out that it's x squared minus, and these will make sense later as to why they are the way they are, I hope. But it's a nonlinear system. So you should see that what we did earlier were linear systems. We are now doing nonlinear systems. At this point, you should see what the difference between the two are, hopefully. And next, I'll talk about why partials matter. So, why do partials matter? This is going to be hard. So, a derivative, if I think about the derivative of, say I had y equals x squared, and I wanted the linearization of that at x equals 3. Well, you would do point slope and you would find a tangent line, right? This would be my x1, my y1 would be 9. My derivative is how I would find the slope. That would give me y prime equals 2x, and my m would be 2 times the x value, which is 6. So I'm doing that fast, but that's review. You guys should be familiar with tangent lines from before. But if I wanted the linearization of that at x equals 3, it'd be y minus y1, which is y minus 9, equals m, which is 6, times x minus 3. So what I want you to see is that a derivative is a linearization of a function. Okay? You with me there? Hopefully you're with me there. I would do a thumbsies here if we were all together, right? But my virtual thumbsies? It's the first time I've done that. All right, so a derivative is a way to find the linearization of something. Now, come back to this. This is a linear system. I know how to create a phase plot for it, right? I use eigenvalues. I use eigenvectors. I then, create my phase plot with that stuff. You guys should be super familiar with that. I just made this one up a moment ago, so who knows how easy or hard the actual eigenvalues and eigenvectors are. But if it's, do it, right? So come down here. Notice this thing. How do I say this without teaching the whole unit right now? This thing, my goal with one of these is to create a big phase plot. The big phase plot has different spots. This one, for example, has 4 different spots that are of importance, is what I'll say now. What am I going to do? I'm going to find the partial derivative of this with respect to x and of this with respect to y. And same thing with this. I'm going to find the partial derivative of this with respect to x and this with respect to y. If this was f and this was g, then what I could do is make a matrix that was f sub x, f sub y, and then g sub x, g sub y, right? So these, and listen, I'm kind of like I will teach you more of this in far more detail soon, but I'm giving you a general, what do we care about? This actually has a name, it's called a Jacobian Matrix. Those of you in multivariable should recognize it. Anyway, I have a Jacobian Matrix right here. I have this matrix that's these partials. This right here, if I evaluate it at the right spots, becomes the linearization of this thing. Now, remember, if I have a linear system, I can create the phase plot. So what I do is I take this thing and then I find the linearization, which is what we call the Jacobian matrix, and then I do my eigenvalues and eigenvectors at all of my 4 different spots that we were talking about a moment ago, and then I get these 4 different phase plots that are then connectable all within a 2-dimensional plane space, and then I get this really nice picture. And actually, I may as well just do it. Okay, so without getting into the details of where any of this would come from, I said that this thing has 4 spots. Here are the 4 spots, one there, one there, one there, and one there. I get a linearization, I get a regular x prime equals ax system for each of those individual spots using partials. And I come over here, and then for this one, I would have gotten a sink, right? I would have gotten a sink node with a vector there and a vector there. I intentionally drew dotted lines here because there would be another half of the vector there, but this would have given me 1, 0, and 0, 1 with exponential decay on both of them. Here, I would have gotten, you should see this if there was an arrow going here, this would be a saddle. Do you see that? So I would have this going out, this coming in, and this one coming in. I ignore the negatives. We'll talk about that later. Here, I also get a saddle coming in, going out, going out. I didn't draw this one because this one is a spiral source. How would I get a spiral source to fit this thing? Well, I would spin this way, and I would spin this way. So this one would actually be a counterclockwise spiral source, and they connect like that. And then they go like this, and then I would have all these different branches. If I was in here, I would go like that, like that, like that, and things would sink into 0, 0 there. And then if I was out here, it would go like that, like that, and like that, and like that, and then I'd see them starting to creep over this way. Draw one more that would go up like that. And this would be the ultimate phase plot for this system over here that I would build, and it's like a lot of work, but I want you to have a big picture idea what's going on, right? I'm using linear systems to cheat my way into be able to do sort of like a tangent line, a linearization of something, but at a whole bunch of different spots, and I connect the phase plots. So real quick, review. What's chapter 7? Oops, undo. What's chapter 7? Nonlinear systems. We know linear systems, they're these. I know how to do them. They look like this. This is clearly a nonlinear system. What do? I linearize it. I do my, quote, tangent line. What's the tangent line look like? And this will be discussed later. It's this matrix right here. I do that, and I evaluate that at each of these different little spots. 1, 2, 3, 4. There's a lot of details there that I already filled in. I had a saddle, I had a spiral source, I had a sink. I connect them all, and you'll learn how to connect them all in this form. And I can create this big phase plot that tells me in general what happens with this predator-prey, competing species, peaceful coexistence of there's all kinds of different things that we can have in biology that we can represent, and we can see what happens in a system. And then say I were to have this thing and I were to change this to an 8, and I would do that by systemically in the population models by changing something or introducing something. What if I introduce something that changed that 2 to an 8? Well, then I could create a new phase plot and then figure out what's going to happen and then decide if it would be a good idea to change that 2 to an 8. So hopefully you are motivated to see this, and I love this stuff. It's awesome, and I'm sad that we're not together doing this, but we're still gonna rock through it, and I think you're gonna enjoy it. So thank you, and bye.